Alright, good afternoon everyone. Welcome to the 10th lecture in COMP1511. Our last lecture of week 5. I guess officially we're halfway through the course. Well done for getting to here. Another half to go. What's happening? Well, next week is flexibility week. So all your courses will not have lectures, not have tutes, not have labs. Doesn't really, so the whole idea about flexibility week, sorry, it's not holiday week, it's not take a break week, it's more let you organize your time and catch up with things and focus on whatever, shift things about to give you some leeway to work on things and sort out things. So we don't have schedule commitments, but there's plenty to do. So what is there for you to do with COMP1511? Well, assignment 1. Yeah, I keep encouraging you to work in assignment 1 in little chunks. It's not easy. There are so many things to get across. Hopefully you're making some progress and keep making progress. And it's, I guess, the most important thing to be working on over flexibility week. It's due as soon as flexibility week finishes. Also, this week's lab and test. This week's lab, we've delayed it would normally be due next Monday, but we've pushed it back so it's due after flexibility week. I would say don't spend much of flexibility week on this week's lab. The assignment is much more important. So I'd get this week's lab out of the way early, or out of the way now, and focus on the assignment. Yeah, things like lab challenge exercises, you can spend a lot of time on lab challenge exercises and they're fun. And that's I'm happy for you to do that if you don't have better things to do. And the better things to do might be assignment 1 for this course, or it might be work for your other courses, e.g. your maths courses. So yeah, try to be smart. Well, honestly, if you've got to university, you've probably got pretty smart about how you allocate your time anyway. But keep doing that. Last week's weekly test, our second weekly test, released in week 4, is due tonight at 8 p.m. So you haven't done that, don't forget, finish that. Remember, treat the first hour just like an exam, all the time pressure, see how far you get in the first hour. It's your way of getting real honest feedback about what you're doing so far. And second, don't panic if you can't do all 3 test questions in the hour. It's designed to put you under some pressure, some time pressure, to prepare you for the exam and things like job interviews and so on. So I'd say, yeah, look, if you're getting 2 questions out or close to 2 questions out in the hour, that's pretty good. I'd be fairly relaxed with that. If you're not getting close to 2 questions out, yeah, I'd keep working hard, but you and a lot of the class are in that situation. If you're getting less than 1 question out or really struggling to get 1 question out in the hour, you should be thinking about all the ways you can keep working and keep improving. It's not, yeah, you're going to have to keep working right the way through this course.
If you're in that position of not having done one or finding it really difficult to get one, that's the point where you really flag with your tutor and say, hey, I've had this issue. They'll be able to give you more advice and support. Obviously, you can always go to your tutor, but particularly in that case, that's a big flag to go to your tutor.
Yeah, excellent point, Tom. So that was last week's weekly test that came out last Thursday. We'll have another weekly test out shortly, but again, it's not due in flexibility week. You probably want to pick a time during flexibility week to do it, just get it over with. But it's actually due immediately after. It's due, I think, the Thursday after flexibility week. As I said, we're keeping flexibility week for you to allocate your work where you see fit, which is sort of the spirit of flexibility week. But we thought we'd schedule some optional extra activities in flexibility week, and we've got some great ideas. Some of the tutors have come up with some really nice ideas. I think we're going to try for 3 or 4 optional activities, talking about extra stuff of various sorts and a revision activity as well. So you'll get announcements about those. You'll check them out. They'll be online, of course, because UNSW is locked down, Sydney is locked down, Newcastle, the Wollongong's locked down, the Greater Blue Mountains are locked down, and we expect to be that way. Well, we know that we've been told we'll be that way for what is week 5 and week 6 for us. So there are no, of course, tutes and labs this week. We're fingers crossed. We're hoping if they get the COVID under control, we'll have face-to-face tute labs in week 7. So if you have a face-to-face COMP1511 lab, we're hoping it'll be back to on campus after week 7. But it all depends, of course. In the meantime, stay safe. Try to keep everyone else safe. Listen to your chief health officer's advice. If you have symptoms, get tested. Try not to infect anyone. So that's, I think, where we are in the course. Of course, if you have an online COMP151 tute lab, it'll stay online after the break. All right. I think, are there any announcements I've missed, Tom? Oh, help sessions. If you need help with the assignment, check out the class homepage. There are help sessions listed there, or check out your email for an announcement about help sessions. Good place to get help with the assignment. Course. Oh yes, I did want to say the very best place for help in the course is the course forum. So it's monitored many hours. We've got Shrey there patiently answering all sorts of questions. If your question can be answered there, that's a great place to go. Students occasionally email me, and I feel very guilty when I notice the email sort of buried in my email 2 days later. So you're much better off going to the course forum and getting Shrey or one of the other tutors to promptly and help you out. Probably give you a better answer than you get from me anyway, honestly. So first stop, course forum. If it's something private and individual, not what's the bug in my program, you can email the class account. They're the two best things. It's best not to email me, just because I get so much email, and emails from all sorts of people often get lost. If you have sent us something important in the email, particularly me, feel free to send us a reminder if you think we should have replied and we haven't. So we occasionally miss stuff. We do try to respond to everything, but let me emphasize again: we try to do everything in the course forum because it works well, and you get answers quickly. And well, in fact, if you're coping well with the course material, let me strongly suggest you try answering questions in the course forum. It's how a lot of tutors get their start. They realize that they're pretty good at this stuff, and then they try describing answers to people and get good at explaining to other people. Incredibly useful skill in many ways. So if you're doing well in the course, think about answering some questions in the course forum, helping out your fellow students. All right. So yeah, I'm going to talk more about today about characters, ASCII, strings, and what we call command line arguments, and explain all of this. We're going to do a little bit of recap, just as usual, and then we'll launch into some new material. First, my recap. What do we talk about? Oh, actually, no, I want to go back, further back, way further back. All right, we talked about, well, yeah, it's nice, isn't it? I mean, we all know, we've all long been told, everything on a computer, in the end, it's zeros and ones. You're watching YouTube videos, in the end, it all comes down to zeros and ones. You're on Facebook, it's all somewhere down underneath every image, every video, every message, everything down there is zeros and ones. And we're sort of seeing, for the most part, it's not the zeros and ones. We mainly talking about them in lumps, numbers, integers. So, and you're seeing that in this course, and you've seen the two actually crucial cases when we want to talk about fractional numbers, reals, floating point numbers. We do it one way, and we'll teach you more about that in COMP1521. And integers we do another way, and integers are actually much more important. So, well, I guess if you're an engineer in particular, or working with sort of numerical calculations, knowing how a computer handles those sort of numbers is important. But most computing generally, it's all integers. So we've seen another crucial bit of the puzzle, an exciting bit of the puzzle really, is how do the individual characters in writing turn into numbers? And the answer is, well, it's a bit limited and mundane. But in this course, we're only going to deal with a real subset of that. We're going to deal with one subset, one way of saying, here's a number for this character. This way is called ASCII. I'd call it an encoding. It says this character turns into this number. And it only does it for a very few characters, 128 characters, and really only 90, about 90. The rest are special. And 26 lower, 26 uppercase letters, 10 digits, what's that, 62 plus maybe 28 other characters and some non-printing characters. So the bad news is, well, the good news is if you're an English speaker, ASCII is great. If you're not an English speaker, you're in the rest of the world, ASCII is not so good, but it is a subset of something called Unicode, and all the lessons we learn with ASCII sort of carry over to Unicode. So we don't have to worry about that. All this stuff we learn, yeah, it sort of will extend nicely. It's good. We can learn in the sort of really simple world of ASCII, and then then we can go on to the larger world of Unicode and coping with, well, maybe your language, for example, maybe your first or second language. We saw single quotes, this new C syntax that said, give me the ASCII code for this character. So you can say single quotes little a, and it gives you the number for a, little a, which is apparently 97, or big A, which is apparently 65, or the digit 0, which is apparently 48. Tom said a good way to think about this, and it's an excellent analogy, is to think about it as a special hash define for characters. So if we didn't have that syntax, we'd probably do a hash define something like ASCII A 97, but that special syntax is nicer. We can just put little quotes there to get the ASCII codes. Don't ever put the ASCII codes in your program. You'll see me do it in silly examples. Don't do it in general. We saw a new function, putchar, to output a single byte is what I'd say, which we can use if we output an ASCII code, the character will appear on our terminals. Just as a side note, the terminal I use, maybe the terminal you use, is actually probably Unicode capable, so you could actually output Unicode and see all the other characters. But in this course we're just going to stick to outputting those few ASCII codes and seeing those characters. That would be something for you to play with maybe after term, in the break between terms, if you want to explore things, is to figure out how to write Unicode from your C program and see what happens. It's a sort of huge time sink. This is one of the things I say, this is really exciting, but after the exams. Okay. So putchar put out a single byte, which you can put out in ASCII code. %C does the same thing in printf. So we can use %C for exactly the same purpose. You're saying, which should I use? I don't really care, honestly. I tell you about both because I know you'll often be looking at tutorials or other internet resources, and you might see either if someone puts up example code in a book, a tutorial, something on the web. So it's nice if I've mentioned both to you. All right. You know I like to explain by a program. So this program goes through. You can look at this loop. So you should be getting that programmer's feel, which is, what does this loop do? And you think it executes how many times? 128 times, and the variable there, ASCII, will have the values 0 through 127. We're printing it out there using a %C. And that'll let us see, my terminal will render that as whatever ASCII character that corresponds to. And we'll put the number there so we know which number it is. And I can hopefully run this. And you can whoosh. Yay. So there's, in all their glory, are all the ASCII codes. And as I said, if you're in a non-English speaking, if your English isn't your first language, you're probably missing some characters. Perhaps characters out of your name, which would be sad, of course. Oh, by the way, if you're thinking, is UNSW's IT systems for students, is my UNSW Unicode capable? No. You can't put Unicode characters in your official name for UNSW. It does let a few people put a few characters from languages like Spanish, which is creates more problems, I think, than it helps. But yeah, all right, that's really my problem, not your problem. All right, so that was the ASCII program. That was lovely. What more then? Oh yeah, we'll come back to this. Alright, so we saw a different input program. So we saw putchar, output a byte. We saw getchar, which is get a byte. So similar sort of job to scanf. Get some input from the terminal. Getchar reads a single byte. Now, if it's reading from a terminal, that byte will almost certainly be an ASCII code. In this course, we don't deal with what I'd call binary, reading binary, so you'll be getting an ASCII code. So getchar will give you a number 0 to 127. Getchar also gives you a special value -1 EOF to say, oh, I couldn't get your character, Andrew. That's a special value. We'll see that in code very shortly. Very shortly. How shortly? This shortly. I've got code here. There is a loop. You'll have to wait till week 7, but in week 7 lab exercises, you will be using this loops like this. You'll be writing programs that read a character and do something with it. And my recollection is it's encryption and decryption. So, which I love because it's sort of the very genesis of modern computing was in World War II and code breaking. So I think it's very appropriate that as you take your steps into modern computing, you sort of track this history in a way. There's a nod to the great history that's of computing there. So you get to do a little bit of encryption in and decryption in the week 7 lab. I should try running this, shouldn't I? What this program called? It's called getchar EOF. Have I got it here compiled? I think so. So I can type in hello Andrew, and those the ASCII codes, capital H E L L O space capital A Andrew and new line will all be read for the program. Now there's actually something we're noticing here. This program has said give me a char. I've actually typed in give me a byte, and I've typed in a pile of characters, so the operating system could already give the program bytes, but it hasn't. The operating system waits, Linux waits until it sees me type a new line. It doesn't have to do that. It does it sort of for weird efficiency reasons. But the end result is no characters will be available until I type the new line. And then they're all available and the loop can execute a pile of times. And there we can see it printing out. And we can see it printing out regular ASCII codes. What I'd call a non-printing, one of these weird special non-printing ASCII code, doesn't correspond to a real character. It's not something we write. Instead, it's a space. The terminal will output a space if you give it an ASCII code of 32. Another one here is 10. The terminal will output a new line, or move output to the next line with a 10. Those are the only two non-printing ASCII codes. Well, yeah, I guess there's also 0, which we'll come to a second. Those are the only two, space and new line, are the only non-printing ones we'll output in this course. We'll also see 0 as a special meaning as well, but very shortly, very shortly. So pulling apart characters, reading them with getchar, outputting them here. Right, that's good. That's very nice. Last bit of recap. I love this program. It's every first year computing course, every first computing course just about shows students something like this. It's a classic thing. So my job here is, given a lowercase letter, convert it into uppercase. Given a little a, convert it to a big A. Given a little f, turn it into a big F. How do I do that? So this this relies on this property of ASCII codes that I emphasized in the last lecture, that the codes for little a to little z are consecutive. They run from 97 right through to, I think, 123 or whatever it is. You notice I don't even memorize these codes, and you don't have to either. But they're 26 consecutive. So if we get a code that's greater than or equal to the code for little a and less than or equal to the code for little z, it has to be a little letter, a lowercase letter. There's no other codes between. And we can get its position in the alphabet 0 to 25 by subtracting the code for little a. So that'll give me a number 0 to 25. Same applies to the codes for the capital letters. So I can just add it to the code for big A, which is 65, I think, and get the result. So I think that's a lovely piece of code. It's nice design there, saying if we get a little letter, do the conversion. Otherwise, do nothing, just return the same character. And then I can embed this in this loop we just talked about, that reads characters until there are no more characters to be read. So it reads characters until getChar says, I have no more characters. Notice here, by the way, this type is in. That's important. Always use that there. Not using in here, by the way, is a classic programming bug, which has been plaguing C programmers for a very long time. Yeah. So my program was called, what was my program called? My program was called uppercase. So let's try it out. Tom's been doing a lot in the course, so we'll send Tom a thank you. So Tom, thank you, you have been amazing. But I'm going to turn it into uppercase to make it much more emphatic. There you go. A thank you for Tom in uppercase. Now, this loop is reading to until there's no more input, but input's coming from the terminal, so I can type as much input as I like. So there's not a finite amount of input, there's not a fixed amount of input. It's possible to set up programs so input comes from somewhere that is a fixed amount, like a file. Next term. This term, well, you need some way to say there's no more input, and the operating system has a very special way of saying that. On Unix-like systems, if I type Control-D, it's a message to the operating system, not a character, it's a message to the operating system. There is no more input. So if I type that now, this will have exited because the getChar here will have returned EOF, which is -1, and the loop will have exited. So that was me typing Control-D. You really want to test out your tutor's knowledge. Actually, they'll need to have done operating system. If you want to test out whether your tutor really understood everything in operating system, get them to do a step-by-step account of what happens when you type Control-D, which you probably won't understand because you haven't done operating systems. It's actually quite complicated what happens behind the scene, but keep going, do our operating systems course, you can understand. But for now, all you need to know is Control-D is special and it signals end of input. Is it Control-D on every system? No, on Windows it's a bit weird. I don't even know what exactly it is on Windows subsystem for Linux. Some Windows programs used to have to type Control-Z, and I'm not sure what the story is on Windows subsystem for Linux. I think on Macs, if you use the command line on your Mac, if you have a Mac, it's still Control-D is the special signal. It's actually configurable. If you hated the character D, you could configure it, but let's not get into that. So beautiful code doing interesting thing. All right, so let's move to some new content. Scroll down, scroll down, scroll down. Keep scrolling. Oh, yeah, useful functions. Yeah, these exist. You might get to use. You could even use them in the week 7 lab exercises, I think. Oh, new type. There you go. So the main types we've seen, let me recap what the main types we've seen are. They are int and double. They're the crucial building block types we've seen. We've now also seen two compound types, I'd call them, types built on the building blocks. One is a collections type, I'd call it, an array. So you can have an array of some type. The next one we saw is a pointer to some type, a reference to some type. And we'll be talking much more about pointers after the break. There's a lot more to say there. There is actually a very special type that we don't actually use as a type, and that's void, which is a sort of it's a type, empty type, but don't worry too much about it. But so C actually has several types which you can store integers in. 5, 6 types you can store integers in. We only use one really in this course, which is int. But we need to see another one now for a special case. So there's another type for storing integers in, and the type is called char. Ignore the name, just think of it as like an int, but smaller. It's usually only 8 bits. Int on our systems is 32. It can vary, but on general purpose computers, the sort we do normal computing, normal programming, it's typically, that's sort of a typical sort of number. You're thinking 8 bits, that doesn't let you store a very big range of numbers. There's not many patterns. 2 to the power of 8 is 256 bit patterns, so I can't store many different integers. It's true. But what you can do is you can always store the integers 0 to 127. So if you need to store an ASCII code, it will always hold an ASCII code. Still don't use it unless there are cases. The only case we want to use char, this type, is for arrays of ASCII codes, arrays of ASCII character codes. Why? You're saying I could store them in an int array. You could, but there's a C library functions, and it's sort of built into C that if you have sequences of ASCII codes, arrays of ASCII code, the type of the array will be this char type. So only use it for arrays, don't use it for individual variables. You can put your individual ASCII code in a single int variable. Alright, so there is a certain sort of beginner C coder who discovers about the char type and thinks, oh yeah, a lot of my variables I'm only storing 0 to 9, -10 to 15, 0 to 20. I could just use a char variable for all of those and save a few bytes. So this code is perfectly valid C. Don't do it. If you want to store a number, just put it in an int variable. There are important and less important and subtle reasons for this, but for now, just take my word, just use int. All right, so let's move on a bit. String. What's a string? Like many English words, it has many meanings. What does it mean in computer science? Well, I'd say, it's being semi-mathematical, it's a sequence of characters. Another way to say is if we have multiple characters together, if you work with computers, you call it a string. So what does it mean in C though? It's a bit more precise definition in C. So most computing languages, it's sort of a very useful sort of thing. So most of your computing languages are going to have a string type of, or some way of doing strings. Everyone wants sequences of characters. But in C, a string is an array of char variables, and it contains ASCII codes. So that's a C string. This array, and now you remember last week, oh, where was it? I have to show you my weird program. Let's recall my, sorry, I like this program. Bear with me while I go back to this program. This program's great. Print array. We wrote three strategies for this function print array they're attached to the lecture slides for Tuesday, but three versions of this print array function. The last one, the weirdest one, was I want a function that prints out numbers in an array. I'm going to do it by putting the numbers in an array and putting a special marker value to say we're done. So the last element will add an extra last element, which is -1. Now, as a consequence, we can never print out -1, so we need a special value we're not using normally. But if we're always printing out positive numbers, -1 is fine. Well, we'll see that short. And there's my code to do that. And it lets me. It's very convenient because when I can just pass the array, and this loop that wants to execute once for every array element and print it out. Just has to say, I'll look at array element 0, is it -1? Look at array element 1, is it -1? And go until it sees a -1. So I can just head down the array looking at 1, 2, 4, 8, 16th, and knows to stop when it gets to -1. Our other versions of this function pass the length or fix the length. So we wrote a version of the function that worked just for arrays of size 6, and a version of the function that worked for arrays of any size, but they passed the length. So this was the last version. Why am I bringing that up now? I can tell you why I'm bringing it up now, because that's how strings work. So strings work with an extra last element on this array of char variables. This extra last element contains a 0. Now, don't panic. You might be thinking, well, wait, what? I can't write out the character that has an ASCII code of 0. There is no character with an ASCII code of 0. In fact, the people who did ASCII said, oh look, we'll keep 0 as a special thing, as a marker, but just like this. So they anticipated this when they were setting out the ASCII codes for characters. They said you can use 0 as an end marker, and C followed up with that. Oh, I fixed that. I'm sure I fixed that. All right. There's an extra slash there. All right. So C string, ASCII codes in an array of char variables. Last thing in the array will be an element containing 0. If you're reading about this online or elsewhere, you might hear that called a null character or a null terminator, or you might see null spelled N-U-L. People write about it in all sorts of ways, but what it really means, and I'm very keen to give you the truth and nothing but the exact truth here, is there is a 0 in the array. That's a C string. All right. And here's, oh, what the hell? These lecture slides are full of typos. I'd like to say it's only this week, but it seems to happen every week. All right. So C has built into its syntax the sort of in the characters of C, but built into the C language is a very convenient shorthand way of specifying a string, and that is double quotes. So we've seen single quotes, single quote, what we say, that means give me the ASCII code for a hash, which might be, I don't know, 49. Double quotes mean something very, very different. If you're a Python programmer, you're saying, what? Huh? Double quotes and single quotes are exactly the same, aren't they? Yeah, Python, yes. C, hugely different. Hugely different. Double quotes means char array. So double quotes gives me a string or an array of char. So this gives me 3 ways to put a single word in an array. Right. The first possibility, that's wrong, would be just to put the ASCII codes in there. That works. So I want to put hello in this array. I've put in the ASCII codes for HEELLO and then the special marker 0 value. That will work. And that will finish up with 6 elements in the array there. C smart enough if I don't say how big to make the array. Finishes up with 6. Alright, I said that works. I also say, please, please, please don't do this. I want to show you what's happening underneath, but it's the same, but don't do it because it makes your code completely unreadable. So better is to say to C, give me the ASCII code for little h, give me the ASCII code for little e, and so on. And this is how you write the special marker value. That turns into a 0. So that's how that's another way to write the special marker value. That does exactly the same thing as the first thing, but it's a lot more readable. I can look at it and go, oh, it says hello. Right, that's a bit tedious to type, and it's a bit error prone, as you can see from me stuffing up further up. So they decided to give you a nicer way to do it. You just put double quotes and the character, and that turns into exactly the same thing as that and that. 6 numbers, which are the ASCII codes for H, double L, O, and an N0. So it does exactly the same thing, but it's a million times easier to read. Well, a million times easier to read than that, 1,000 times easier to read than that. It's nice. Use it. Oh, alright. So this is one of my I love these programs. You don't have to, but I love them. We're going to go back. I love programs that do the same thing. 5 ways to do the same thing, to show equivalences. I think equivalences are a great way to learn about different concepts. So here we have my first version of a program. Now you're saying, what does that print? I think there's probably a comment that prints it. Oh no, there's not. So who knows what it prints? So we'll compile it and run it. Oh no, I already have compiled it. Let me change over to the directory for this week. Let me run it. Already compiled it and run it. And it prints out a message there. And you can get into this and think, that's a new line. Oh, that's a space. Ooh, 33. Oh, that's an exclamation mark apparently. All right, so we don't do this. This is bad. Don't do this. Do this and your tutor may cry on the spot. We don't want that. What can we do that's better? What about this? So this is how taking advantage of single quotes. Our friend single quotes does exactly the same thing, but uses C to say, give me the ASCII code for capital A and so on. That works. Writes out exactly the same thing. Let me demonstrate. All right. Okay. Oh, we're missing an exclamation mark. I said they did exactly the same thing. You could have a put char exclamation mark there. I won't bother with that. How can I else? What else can I do? All right. This is sort of a stupid program, but it's a halfway program to doing other things. I've decided to put the ASCII codes in an array. I thought I fixed this. I don't like that case. I prefer it. Yeah, but anyway, I don't like the way that variable name's written. I thought I'd fix that, but apparently not. Don't worry about that though. Creates an array of size 14, puts the ASCII codes for the 14 characters you want to write out in it, and then uses a loop to go through the array and put out the characters. Now, yeah, that doesn't look like a win, does it? It seems a bit stupid, and it is, but it's a stepping stone. But it is important you read all of this and see that and figure out, yeah, I know what that does. I know what that does. That all makes sense to me. That works. And it does. Okay. What about my next version then? Oh, all right. Yeah, it's formatting a little weirdly, but here's my next version. Really the same as before. I've done the initialization like this. So that's a bit nicer. I've initialized the array in one go rather than 14 assignments. This is still the same. So that's version 4 of the program. Yes, there are 3 more versions to come. It does the same thing. So that's the same program yet again. Writes out the same thing. What about my next version? Ooh, that's almost the same, except I've made this. Oh, have I gone one too far? Sorry, where am I? Bear with me. Help. This is version number. All right. No, we saw that one. What we want is this one. All right. Because these values are small numbers, we can use an array of char variables, and this is what C does in a lot of places. So we've initialized an array of char variables to 15 values. The 14 things we want to write out, and a 0. And we've changed my loop to say stop when you see the 0, but it goes around writing out the ASCII capital A, the ASCII little n, the ASCII little d, the ASCII little r, the ASCII little e, the ASCII little w, and so on, until it sees this 0, which it doesn't write out, it exits. So it works its way through this char array. Let me just demonstrate that those versions all do the same job. Alright, 2 more versions to go. I think you can guess what's coming now. There's a nicer way to write this. That's what I just talked about. There's a nicer way to write all of that, and that's this way. So it does the same thing, puts 15 things in the array, the 14 ASCII codes there, and an extra 0. So it's exactly the same program as that, but instead of writing out what these things are explicitly, we use the lovely double quotes shortcut in C to say this. Same loop to write it out. Go through the array until we see the 0 and print it out. Perfect. All right. All right. One more. Uno mas. Oh. Same initialization of the array, but we're using. Oh, I did fix this. This is. Oh, I haven't. Now I understand. All right, all of these are fixed in on the class web page, but I forgot to copy them into the CSE system where I'm working. Let me fix this. That's important. Actually, I fixed this. So the 2 things I changed was I called this variable ASCII code, so I like doing it in that case, and that's the case we recommend for this course. And I wanted to use a different function. I wanted to use fputs. We'll talk about fputs in a little while, but it's a function that, given an array of ASCII codes terminated with a 0, will output it to the terminal. I'd say output it to standard output, but you can think of that as writing it out on the terminal. A different way to do it is with printf and %s. Printf %s, what have we seen so far? We've seen %d, expect an int, %lf, expect a double, %c, expect an ASCII code in an int variable. %s is expect a char array. You're thinking %s, char array? That doesn't make sense. %s, the s is for string. But what it really means is the corresponding following variable should be a char array. All right. And printf does that with a %s. So that writes out the thing twice. So but we'll try that out. Oh, yeah, that's an extra new line there appearing, which will avoid. We'll recompile that. That's a bit of a worry. Oh, spot my mistake. DCC should be nicer there, shouldn't it? Right. So there are two ways. If I have an array of ASCII code with a terminating 0, there are two ways to dump it all out to standard output. Nice. There was a program then I wanted to change. Let me show you. Now I know how to write out a string. It gives me an interesting possibility. Let me show you this. It was in last week's. Sorry, it was it called powers.c? I think it was called powers. Oh, look here. All right. Now, yeah, it's a nice example. So this is a bit ugly because we're thinking, oh, I'm almost doing the same thing 3 times over. Programmers hate that. It's just frustrating. You want to just do things once. You want to do it right. How do I do that? I'd like to put that in a function. Let me, oh, we were halfway through modifying this. We'll make this back to the way it was. And we'll dump the new version of the function. So that's what we had. How can we turn this into 3 calls to the one function? We can now because we know how to write out a string. So we could get that. And can we use the same thing to write out e squared, e cubed, and e to the 4th as we write out pi squared, pi cubed, and pi to the 4th? So can we construct a function that will do that job? Can we generalize it? All right, let's start with. Get that code. It's a nice example. This is, we end up doing this sort of thing a lot as we code. All right. What are you doing to me? I guess in my function, I call it print powers. We'll write a void for one first that takes no input and just does this job. And see if we can substitute that in. That's not very good, but it's often a good thing to do to start. We've got rid of that powers 1 1. Having a good day. Let's copy the line, paste the line. Gedit, not my favorite editor. Good for students, but most students finish up moving to another editor, but all sorts of different editors. Some people actually stay with Gedit. Some people, you can extend it and program it. It's not bad. Oh. Oh no, I need 3 parameters, don't I? Oh no, I don't. That's all good. Coding here. This is nice to show you because this is very typical sort of things you finish up doing. I'm moving this over here. And I think, oh, we said as well that these names weren't good. I think I put better names in the code I linked to the class website. And we ran the 1511 style program, didn't we? Which pointed out that these S, C, and F were not good names at all. Alright, have I actually managed to get that to work? Oh, so close, so very close. Line 33, extreme. Oh, and that's right, there is an extra brace. This time for sure, we'll put it in the variable, put it in the file powers. We'll see if that works. Alright. Oh, we haven't called it though. So this is just the sort of thing you may be doing with your assignment as you try to construct functions. So I'm halfway there. I'm writing sort of weird functions, getting halfway there. Print powers. Let's try that then. Oh, this time for sure. All right. Okay. We've moved the code to print off E into a separate function. It only does, this function always prints off the powers of E. So we'd like it to print off the powers of anything and then use it for all three cases. So we'll have it pass in X, work out the powers of X, and then print them out. And then my plan is to call the function 3 times to print the powers for pi, print the powers for, actually we're doing E first when we print the power of E, print the powers of pi, and print the powers of 42. This is also not quite right. Oh, I don't need that SC and F there anymore. But I think I'm getting closer. So I'm moving closer to a better design. I've simplified things. We've got this code here. It's not quite right, but it's happening once. This is going to be exactly your thing. It's really hard to learn how to create functions, manipulate them. So we don't be discouraged if you can't get them right first go and your design's not quite right. It's perfectly normal to write them and then have to change how they work and think about them again and try again. As long as you're moving forward, keep thinking. And it can be a good idea to talk to your tutor. Sometimes just a conversation with your tutor can tell you, oh, add another argument, or think about adding a function that does that. So we'll try this, which is almost there, but not so much. Oh, my type is wrong there. It's complaining because I've said powers 1 input, 1 argument, double. Up here I've said powers no arguments. That's the weird way of writing no arguments. I'll change that to be consistent. So all of this here is really just saying, oh Andrew, your program's inconsistent between line 8 and line 20. It's perhaps be nice if the C compiler said that. And I've misspelt print powers once. Ah, there we go. Ah, we're good. Oh, so everything's great. These are the powers of E, these are the powers of pi, these are the powers of 42, but it's saying E squared, they're all E squared E, it's saying E here every time. We want to be able to say what they're the power of, and that's the next part. And here's where I can use my ability to print a string. I can put a %s there, watch me, and then put the name here and pass through a string, which is whatever the name of this is. And we'll pass it as the first parameter. We'll say char name. There's a few ways to write this. I think that's probably the best way for now. And here we'll say, oh, that's E, that's pi, and that's 42. Will we say that? No, we might say the string just containing 42. And we'll say, we take two parameters, the name of whatever we're writing the powers of, and the value. And that now should give me a really nice function. So close, so close. What have I got wrong now? Oh, yes. Inconsistent again. Again, that's sort of normal sort of programming. I accidentally type something, weird mess of messages, but it tells me what lines to look at, and often you look at the lines and say, oh, that's it. If you stand yourself staring at it for ages, that's a good thing to ask in the forum. Don't post all your code, particularly for the assignment. You can post a tiny amount maybe, or you can make forum posts which are private only to the tutors. Do you want to add code in there? Tutors, if you auto test something or give something, tutors can look at it. And look, my beautiful program now writes out e squared, pi squared, 42 squared. It writes out whatever I want as %s using this variable I've passed here, this array of char. Look, I say it's an array of char. And I pass it through there. Here I give it the arrays of char. It's beautiful. All right. One thing to be aware of is what really gets passed through is a pointer. So I can actually write it like this, and that would do the same thing. So if you look up code elsewhere, you might see it written like that. It means the same thing. Because when an array gets passed to a function, it gets turned into a pointer to the first element. It all works the same. You don't have to worry too much about it, but that's what happens. All right. I hope you like that example. I'm going to take a 5-minute break. I need to stop talking for a little while, but we'll pause for 5 minutes. It's a good chance for you to get up and stretch, look outside at the rather miserable weather, and then focus on something else, and we'll be back in 5 minutes. Hi everyone, welcome back. Apologies, the break was a bit longer than I wanted. All right, let's move on to another topic. Command line arguments. So what are command line arguments? They're another way to give a program information. So far, we've just seen one way to really give well, I guess we've seen two ways to give a program information. One is we can put the information inside the program itself. It's not very satisfactory. We do it a lot when we're debugging. And we'll do it. So we do it when we're learning to program quite a bit. It's not a very satisfactory way to do things. So we can put information embedded in the stuff of the program. But more likely, we get information from the terminal, so we read it in from the terminal using scanf. So is the way we've seemed to read an integer. So that's the second way we've seen to get information. We put it in the program, or we can read it from the terminal in scanf, get a number from the terminal, get a floating point number from the terminal. We've just seen how to get characters from the terminal. There is another possibility, and that is to put extra words on the command line when we run a program. Extra words, really extra strings. So here I'm running a program and I've given 5 extra words, which are both letters and digits. They can be anything. If they're weird characters, you may need to do may need to warn the shell that they're what you want done with them, but don't worry too much about that yet. Come and do COMP1511 with me and we'll talk endlessly about that sort of thing. But that's for next year. Program, extra words of information. How does the program get at these? So that you don't get them with scanf. These not scanf. They're not on what I'd call standard input. They're passed in another way. Now you have seen this before, by the way. Let me show you. You've seen it before here. Look here. I'm running DCC. I'm running the program DCC, and I'm giving it 3 extra words to tell it more about what I wanted to do. So I'm saying DCC compile file powers.c and put the output in the file powers. So we've already actually used command line arguments, even though we didn't know about it. How do you get at them from a C program? Let me show you. We've been keeping a secret. Sorry. Actually, we've been keeping lots of secrets. There's enough for you to, you don't want to be sort of washed away in this gigantic flood of information. So we try to limit the important stuff, so you can try and get your head around the basics and move forward without your brain exploding. So one of the secrets, a small secret we've been keeping, is there's 2 ways for you to define the function main. It's a little weird, really. Main's a very special function because it's the one that starts a C program. So you can define main, the function way we've been doing all along. Yeah, that's okay. But there's another way, which is this. You specify 2 inputs, 2, I'd call them arguments. One is an int, argc. This is actually, it's called argc because it's given the argument count, the command line argument count, the number of words that were typed in. There's a trick here. You'd look at this and say, oh well, argc, argument count, will be told 1, 2, 3, 4, 5, but there's this one as well. It gets told about the program itself, so it actually will be 6. We'll see that in a few programs. So it's a count of how many command line arguments. What about the words themselves, the command line arguments themselves? It's in one, we usually call this argv, which is a contraction of argument value. So argc is a contraction of argument count, command line argument count. argv is a contraction of argument values, or command line argument values. Oh, and the type looks really weird. Yes. What does this mean? it means array of strings. It does look weird. So you just have to write it like this. You're saying, oh, what happens when my brain freezes and I don't remember that in the exam? That's the sort of information we give in the cheat sheet for the exam. Students don't fail the course because they forget that. We also don't give you marks for remembering that. We give you marks in the exam for being able to code, not for remembering little bits of information like that. Sorry. Alright. Oh, let's try it out in code. Let's rather than show it on. Let's show you on doing. All right. I want to. Oh, this one's in the wrong directory. Where are we? We'll go back to directory 10. Oh, well. Let me just get rid of some of these. These are annoying me. I opened too many files. Yeah, we're done with powers.c and print array. All right. Oh, I don't have it. All right, I'll have to code it up. Let's use this as a starting point. Don't worry. Let's code away. Oh, I'm not sure what's happened there, but let's change this to print command line arguments. Save. And we'll change, so that's the main we've all grown to know and love in the last 5 weeks. This is the new main that you can use if you want to work with command line arguments. If your program doesn't, you don't have to use it. It's your choice. And let's just print out argc equals %d and run it and see what happens. Oops, let's spell argc properly. We'll ask the C compiler what it thinks of my program. We'll run my program. It'll tell me what argc is. If I run it now, I've given it the command name and 1, 2, 3, 4, 5 extra arguments, and it should say argc is 6. Let's try and give it a lot of arguments. See if we can get the argc up to 10. So I've put 9 words on the command line. Argc is 10. So no extra arguments, argc is 1. 5 extra arguments, argc is 6. 9 extra arguments. Let me show you if you put numbers there. You can put numbers there if you want. Something similar will happen. And it sort of groups them depending on whether you put spaces between them. So that will be argc is 2. 2 separate command line arguments. The rules are more complicated, but they're not the point here. Alright, let's try this out then. Let's print some things out. Let's print out argv0, the first element of that array. argv0. And let's print out the second element of the array. There are two things wrong there, but let's try and compile and see what happens. Alright, good. Lovely compiler message there, pointing out an inconsistency, something that must be broken. I'm saying printf %d, and I'm putting this here. The compiler is saying enter it. %d means print out an int, and you're giving me argv1, which is a string. It's an array of char. This is really an array of char. Well, really, it's effectively an array of char. So array of char int, they just don't match. I don't know what that's going to do, but it's not good. So don't ignore that. Work out what to fix it. So if I want to print out an array of char with its little 0 terminated, I can do that. And the command line arguments, yeah, we didn't mention that there. Yeah, they're supplied in that 0 terminated way that C does strings. So they come in, command line arguments come in as an array of ASCII values with a little 0 terminator. So we can use %f to print %s to print them out. We could write our own code as well. You can try that as an experiment if you like. But that should compile. Alright, let's try it out. Why am I doing that? What's wrong with it? Why is my P key not working? Why is my P key not showing would be more the point. I don't know what's going on there at all. We'll put it in the file called A, which will help. I can hopefully run like that. Oh, well that's weird. I've gone to print that command line argument and it's printing out as null. What does that mean? I don't think that's a good thing. What happens if I try to print out command line argument 2? Oh, that's weird. All right. Now, I'm doing a bad thing here, which I shouldn't do. I'm accessing command line arguments that might not exist. Let's pass them in as though they exist and make them exist and see them coming through, and then write better code that does the right thing. So let's write 2 words. Alright, so that's command line arguments as it should be. argc is 3. It's saying 3 arguments, program name, and the 2 extra words. Program name, 2 extra words. Print it out. But you should always look at what's in argc before you try to access these. You don't know if they're there at all. And you get errors or weird behavior like this. It's actually printing out some of my environment because I'm accessing something that doesn't exist. So what would be better? What about something like this? I could do it with an if statement, couldn't I? If argc greater than 1, print that one. And you often see code like this that checks its argument count and does different things based on how many arguments it's got. Pretty often it needs arguments, so if you give it no arguments, it'll say give me arguments. Maybe it needs exactly 3 arguments, 3 things specified in the command line. And if you don't give it 3 things, if you give it 5 things, it'll say no, I need exactly 3 things. If you give it 2 things, it'll say these 3 things. So I could write code like this. Which will print out command line arguments only if they exist. So I've got 1 command line argument that prints out just 1 thing. I've got none, prints out none. What if I've got 3? Now, hopefully you're starting to get used to loops. You're thinking about this. I could do this with a loop. Loop variable, index the array, add 1 to it, loop. Loop, Andrew. That's hopefully what you're thinking. Alright, let's try that then. So we can see. Let me see if I can get this right. While I is less than ASCII. I think I can have a loop that accesses 1 by 1 all my command line arguments. We'll print that as argvi. What's my plan here? Put I here. Put I here. I'll use an I++. There we go. That's my plan. Loop through printing out the command line arguments 1 by 1. What can go wrong? Oh, maybe nothing. Right, try it out. 5 extra words. 5 command line arguments passed there. Works like a charm. Alright, okay. Beautiful. What now? Alright, I think there's a few things I wanted to show you. Let me just refresh my memory with a slide. Exactly what I was thinking. Alright, what we're given on the command line argument, each command line argument is coming to us as an array of char. Often we want to turn that array of char into an integer or maybe a double. It's a common programming exercise for students to say write code to do this from first principles, but they're actually built-in library functions. And the slide is just broken. Not having a good day. So there are library functions. There's 2, a to I and a to f, which convert strings to integers and doubles. And there's more powerful functions called str to L and str to D, which do the same job, but they have more features. A bit more complicated as a result. They do error checking, and they handle, in the case of str to L, they handle other bases. Let me show you examples of those. That's perhaps nicest. Let me show you. Yeah, suppose I want to just sum up. I want to put some numbers as extra command line arguments and just have the program print their sum. So you're thinking, your first thought might be to do something like this. Add a variable called, I'll call it sum, and then print it all out. There we go. Beautiful little program. What's wrong with it? There's two things wrong with it. I'll ask DCC. Oh, and I'm sorry, I've overwritten the previous program. That's sad. Let's call this sum arguments. Let's see. Oh, three things wrong with that one I didn't notice. Let's fix that. DCC will still complain about the other things, but it's often worth just recompiling. You fix one thing, it's worth recompiling. So I fixed the silly typing mistake, but I'm left with a deeper problem. It's this. Sum is an int sum. And I said sum plus argv I. What is that? It's a char array. So it's really a char array. It's one or more ASCII codes in an array. You can't put that into addition. It's possible. Yeah, we're thinking, yeah, this char array probably contains the ASCII codes for digits. You can look those up. But C doesn't work like that. It doesn't know how to turn a char array of ASCII codes, even if the ASCII codes are those that we use to write numbers, it can't turn that into a single integer. But there are library functions that can do that for you. And as I said, it would be a nice programming exercise for you to write code to do that, which we won't do at this point. And one of the simpler function I showed you is one called A to I, which takes a char array and looks at the values, and they should be digits, and converts it into the corresponding integers. So it could be the ASCII codes for 10000000, and it'll give you back the int for 1,000,000. There's still a couple of things here to be fixed, but let me show you what DCC says about that now. Oh, I haven't saved it because it will give a different message now. So many messages. You might need to add a prototype for A to I. You're calling function named A to I. I don't recognize function named A to I. What's going on? What I forgot was, and you'll make this sort of, look at it, it's a horrendous mess of error. It's really a simple mistake. And DCC is actually better at reporting these than any other C compiler you'll use. It's still not doing very well there, is it? A to I is actually defined in another include file called stdlib.h. You're saying, why? It just makes my life harder, Andrew. Yeah, C's not really designed well in that respect for first-time programmers. So we have to add that. Again, we give you for exams, for example, a cheat sheet telling you that. It's not something we expect you to memorize. So A to I is coming up there. I could have found it, by the way, by looking at the manual entry for A to I. I've said manual entries, lots of stuff I don't need to know, mixed with a few crucial things. Look there. Crucial thing is hash include stdlib.h. Okay. This time for sure. Saved. What can go wrong now? Oh, I'm not using the value here. Stupid mistake. Must be right now. Oh, interesting. DCC is not doing its job there because there is an error, and an obvious error still in the program, which it's not picking up, but will show when we run. You can see what you can spot. Classic error, simple, important programming error in this program. DCC hasn't spotted it compiling the program, which is a weakness of DCC. It's disappointing, actually. It's not telling me about the problem. It will pick me up when I run, but it's always better if you can be told about when you compile before you run. Let's try running. We'll give it the arguments 23, 7, and 12. I hope it prints 42. Yeah. Oh, that's yeah. All right. Classic thing here, isn't it? All right. So this is where you've got to be brave. This is where things aren't as easy as perhaps they could be. There is an error in your program, but the reporting of it is not great. If it's any consolation, DCC is 10 times to 100 times better at reporting these things than C compilers can be. So it's set up to really help you as much as it can, but not helping enough here. We've got this line here. So we've got there, or there in my code, and it's saying problem. Something, execution has stopped. Why? Uninitialized variable accessed. All right, you've got to work through these things slowly. Look at that line. What variables are on that line? Well, there's only one really. There's sum. So sum is uninitialized. Now DCC, when it stops, it actually pokes into your program, tries to find variables and tell you what's happening. And it says, oh look, it's telling you ASCII, and it's telling you I, and it's telling you sum, which is a weird negative number, which doesn't seem right. So something's going wrong with sum. Also, let's work backwards. Sum is here. Sum had n added to it every time around the loop. Oh, look up here. I forgot to put 0 in sum. Fix that. And we have a working program. Oh, seems good. Seems right to me. Alright, who can sum up the first 10 integers? First 10 positive integers? 55. Great. Alright, so that's doing the conversion of this string here into an integer. A conversion between types. And we could do this ourselves. We could look at the ASCII codes and convert the individual ASCII codes and work out what the corresponding number was. But not yet. Not yet. Alright. I think I'm going to look at my lecture slides, but I think I want to try a different example now. Oh, we saw that. Right. F gets and reading a line from standard input. Well, I think we can wait for that. We'll come back to that. I think that might have to wait for the week 7 lecture. But what I'd like to do is look at pulling apart the characters of command line arguments. So the suggestion I've got is passing 2 words on the command line and trying to test if they rhyme. I'm not exactly sure how to do this, or maybe seeing how close they are to rhyming. So my first thought is I will go through and see in how many places they have the same letter, and that will give me a rhyming score. So we'll go through and count how many places the 2 words have the same letter in the same place on the command line. Alright. So we'll change name. We'll call this rhyme.c. Save it. Alright. So let's do it in the classic way. First we should check we've got 2 arguments. So let's do something like this. There are better ways to do this, but let's start with something simple. We'll print a message. That's not the best message we could do, but that's a message. It's showing you the good structure, if not a good message. So we check how many command line arguments, and then we want to stop if there are not 2 command line arguments. We can't go any further. This is a program that needs 2 command. Otherwise, we'll call a function with the 2 words. Call a function score, maybe. Actually, we'll call it rhyming. No, rhyming count. That's how hard command with good names. Rhyming count. Score equals rhyming count. Yeah, I'm not sure if this is a good way to test rhyming. And in real programming, that's often the way. You don't know what code you're going to write. You often write code to explore. You write the code, run it, see what it prints, what it produces, what it calculates, and that suggests to you different ways to explore, to write the code. You don't start out with a problem like a COMP1511 lab exercise, which is print the 5 prime numbers between 10 and 100 or whatever. Or, you have to explore. So we'll try doing that a little. We'll pass the 2 words we were given, which will be in those. In fact, like that. And then print out the score. How about that? That's my plan. Now let's keep going. Let me show you a nice trick. Alright. Let's get this and work out what our function is going to look like before we fill in its. So this function is going to return our rhyming score, and it's going to take word 1 and word 2. You're saying, what about the lengths of the array? Remember, these are these funny arrays of ASCII codes, and we know we've reached the end when we see a 0. So that's what's done with argv, and that's done in a lot of places in C. When we use double quotes, that's what you get as well. So a good thing to do is try and work out the overall structure of your program. You haven't worked out what's going to go in this, so you can just return, say, 0. And then you can compile your whole program, run it, and then and make sure it all makes sense, and then go and fill it in. You remember, one of the keys to success is if we can take steps. Take a step forward, compile, make sure it's legal C, make sure what we've got in place works. If we can compile, run, and check bits by bits, that lets us move progressively towards a goal rather than trying to take a giant step and maybe stepping into 10 problems at once. This way maybe we can tackle 1 problem at a time. Alright, so this is called rhyme.c. gedit's telling me I haven't saved it. Now I have. And we're good. Oh, and it's telling me I've missed that printf. Ah, alright, give you 2 words. Alright, what 2 words we're going to put in there? Cow and dog. Rhyming score is 0. Alright. So we need to now fill in this function. Oh, I guess I've forgotten an important thing, key part of a function. Perhaps the first thing you should do for the function is what it does. Right, you might not say this if you're expecting the person reading it to be a proficient C programmer, because that's the case for all C programs, that char arrays ended with zeros. But let me be super precise. Right. That's what I want to do. I have a statement of what I want to do there. I'm also telling the important thing with functions is to tell the caller what they have to do, what their job is. So the caller's job for this function is to supply 2 words in char arrays ended with zeros. Am I doing that? Yes, I am. So I'm good. And I'll get back a score, which I'll print out. So time to fill in the function. Going to need a loop variable. Start at 0. Yeah, it's going to be while something something finishes. We'll increment the loop variable. All right, but here, while I less than what? I don't know. I less than what? There's no I less than, is it? We don't know the size. We don't know the size. We just know there's a 0 at the end. We saw that before, so we can say while word1 not equal to 0. Now what do I do? I need a test. Yeah, I have to think about that. Oh, I need a test there. All right, and I guess I'm gonna have to keep a count. Call count. And if they've got the same letter in the same position, increment it and return it. That's my plan. And I can do this. All right. If word1 I equals word2 I. Oh, we're 2-dimensional arrays. It looks like 2-dimensional arrays. Deja vu for assignment 1. Alright, so word1. Oh. Yeah, I got it wrong. It's word1 I. Yeah, I'm not thinking it here, is it? It's easy to get yourself confused. If word1 I. It's not 2-dimensional arrays. What am I thinking? So, yeah, try and keep everything clear in your head. I've confused myself there. Any way you can stop confusing yourself, that's really the important thing, before you worry about confusing other people. Okay, that's good. That's better. So they're both char arrays. We go through the char arrays checking, and if they have the same letter, what do I mean letter? Same ASCII code. Got to really check, won't it? All right. What does DCC think? Oh, so close, but you've got a semicolon. What does DCC think now? Ah, you spot that one. How come you can spot that one but not the one before? Really, DCC? It's pointing out to me I forgot to initialize that variable. Starting to seem every time you declare a variable, it might be better to initialize it. And some programmers like doing that. Wouldn't argue with it. I don't normally myself unless there's if it's not necessary, but certainly wouldn't argue with it. Alright. Rhyming score is 1. How about we try cow and cog? Oh, I've got one. What about cattle and battle? Oh, look at that. Alright. I'm not sure that's a good measure of rhyming. Don't go running to our linguistics faculty telling them this is a good way to calculate whether words rhyme. But we have got a nice piece of C programming there. Now, we're running out of time together today. I've been a little slow, sorry. Don't worry, we've already got through, I think, what you need for the week 7 labs, and we'll revisit it on the Tuesday of week 7 just to try and recap something similar to the labs, just to get you in the mood for week 7 labs. But there's a huge bug in this program. There's a really nasty bug in this program. I've said over and over again, and I'll keep saying it, every time you use square brackets, you should be asking yourself, how do I know that that array index is valid? And it gets tricky with strings. It does get tricky with strings because we never have the length. So then we've got to check, am I proceeding through the array carefully and checking that I haven't gone past the 0 in the array? Or if I get to creating arrays of ASCII codes, have I always put a 0 in the array? So this string, where was this string created? Well, C does it somehow for it and gives us an array of ASCII chars containing the words on the command line, argv1 containing cattle, argv2 containing battle, and we're assuming it'll do the right thing and put the 0 there. So I think we're pretty safe in assuming word 1 has that 0 on the end. And we're checking out element 0, element 1, and so on. So I'm seeing pretty safe here. I can't go past the 0 on the end. C has put a 0 on the end. I can't go past it. This looks safe to me. What about that one? How do I know that's safe? There's a 0 in the other one, array. Where would that happen? What happens if word 2 is shorter than word 1? Let's try it out. Do cattle and bat rhyme? That should print out rhyming score is 2, I guess. What does it print out? What happens there? Can you figure that out? I'm going to hit return. Hey, it's not meant to do that. Surely there's an error there. DCC's not picking it up. That's weird. So that's interesting. So we're using an invalid array index there, and this is normal in C programming, by the way, that an invalid array index is going to be picked up. DCC turns on extra checking, and it's meant to pick up that this is an invalid array index there. For weird and special reasons, it's not picking it up. All right, but we'll actually try and access. We'll go through, try and check if element 5 of bat is equal to E, and that's doing something different. There you go. Alright, so what my code should be, what correct code would be here. what would correct code be? Would be to check we don't code past a 0 on the second array either. That's now a safe program, a correct program. Just still going to do the same thing, but safely and correctly. Yeah, it's a bit scary, isn't it? There was a runtime error in my program. It did unpredictable things, and I didn't know. And this sort of thing underlies a lot of the security problems and other issues with programs in the world. All right. I'm going to ask Tom if he's been scanning the chat. Oh, a big shout out to Adam, who's been very busy answering all sorts of good questions in the chat. So thank you for both the questions, everyone, and the Adam for providing the answers. And Tom, is there anything in the chat I need to be addressing in our last minute or two?
I think most of the questions have been ably answered by Adam, as far as I can tell.
So yeah, Adam's feeling sort of more advanced questions as most I can see, which is great. Sort of people thinking about the implications and things and exploring, which is just what you should be doing, but not things I necessarily need to cover, I think.
No.
So we're going to come back to this example. I'm going to modify it to be more elaborate, and we're also going to modify it then to get the words from the terminal rather than from. So we're going to show you a couple of versions of this next week and refresh you before next week's lab exercises where you manipulate this. Tom, anything else we need to tell students today other than wishing them a happy Flexibility Week? Happy new financial year, everyone. Do your tax returns.
Yes, I think, the main thing is just that lectures, tutes, and labs aren't running next week, but help sessions are, and we'll have some replacement stuff. I think we've scheduled most of it, but it'll go up in an announcement tonight or tomorrow as to exactly what's going on next week. Other than that, check the due dates for everything because they're a bit different to usual. But apart from that, have a good week. Have a good Flexibility Week, I suppose.
Yes, happy July, everyone. Welcome to Flexibility Week. Welcome to week 1 of lockdown in Sydney, Newcastle, and beyond. Unless you're a remote student. All right, so I'll talk. Well, actually, no. I think I will be joining you for one of the Flexibility Week sessions. I think I'll be one of people talking about revision, probably. Well, actually, I'll tune into the other ones, but I think we're going to try and get a few different voices happening for some of the optional presentations in Flexibility Week. They should be great. All right, nice to have you Nice to talk to you all. Yep. Next lecture, next tute lab. So no lectures and tute labs next week. Week after, week 7. Talk to you then. All right, and we're out.